All right, so today we're going to do an absolutely cool, huge, awesome application. We're going to discuss linear regression. So I'm going to give you a big picture view first of all. It's quite possible you have done this in another class. If you've had statistics, you certainly did this. You might have done this in a pre-calculus class. That would be about the only other place. Now, regression is not the same as polynomial curve fitting. The idea of polynomial curve fitting is I give you a bunch of points and you give me the polynomial that passes through every single one of them. Regression is a little bit different. Regression means that you're working backwards. If I gave you the equation of a line, you could tell me all the points in the world. Right? You can tell me on and on and on. If I give you 2 points, you can work backwards and tell me the equation of the line. That's a higher level of reasoning. That's a harder problem, isn't it? Starting with the points producing the line. Starting with the line producing the points is easy. So what linear regression in general means is that I give you a bunch of data points, and the idea is that we sort of see a loose linear pattern of the points. There is no line that passes through all of them, but there's going to be a line that's closest. Let's just say that. So the idea of linear regression is we're going to, starting with a bunch of data points, what is the line that is the closest? So we usually refer to it as the line of best fit. A lot of you have heard that term before. Now, if this is not a linear pattern, then we wouldn't be looking for a line. So in a pre-calc class, some of you may have done the logarithm of best fit, or the exponential function of best fit. There's different versions, the parabola of best fit. We're just interested in the linear, okay, the line of best fit. Knowing there's no one line that passes through all of them, so the idea is this. If there is a line, let's say it's that one, that's closest to all of them, then what I'm really doing is saying, okay, this has an x comma y, okay? If I use the same x value, then there's going to be a distance with the y's. If I had the perfect line in a sense, then all the y's distances probably add to 0, right? Pluses and minuses. But I could have a lousy line with the y's with that sum being 0. So what we do is we square that distance. So if you've had statistics, it's a version of variance. I square the distance. And what I'm looking for is the least squares. So when I add up all the squared distances, I want the line that has the least squares. So linear regression is often called the least squares regression line. Some of you have heard that term before. That's what it's called in stats. You'd never actually see it demonstrated in stats. You'd just be given an equation and plug and chug without knowing where anything comes from. So what we're going to do is derive the equation of the line using matrix algebra, because that's actually how it's done. In a stats class, you don't do that. You only use the final results of the matrix algebra. You don't actually do the matrix algebra because that's already been done for you. So the idea then is that I believe there is a line. Okay? So let's suppose I have the following data points. I have x1, y1, x2, y2, xn, yn. I'm going to make one simple assumption, that all of the x's are not the same number. There's at least one x that's different from the rest. Why would it not be interesting if all of the x's were the same? Why is that uninteresting?
Vertical line.
That'd be a vertical line, and there wouldn't be a line of best fit. That just means my answer is a vertical line. That's not really interesting, right? Because I couldn't give you the equation. That'd just be x equals a constant. If every x coordinate was the same, that means all of these points are on the same line, and that would not be a linear regression problem. Because in a linear regression problem, it's actually not really possible for the line to pass through any of the points. It's going to be close to a lot of them. Okay, so we'll assume all the x's are not the same. Can I repeat x values? Sure. So the first thing I want you to understand is I have reason to believe there's input-output, cause and effect. We'll talk about that just really, really briefly, because in this class our goal is to find the equation, not to explain the background of the statistics. So x might represent, let's say, years somebody's worked for the company, and y might represent their income. So it seems reasonable if I work longer, I'm going to make more money, that there might be some linear relationship. Okay, that would make sense. Okay? Maybe X represents the midterm score and Y be the final exam score in a particular class. It seems reasonable that they would be somehow related. So the assumption we're going to make is there actually is correlation. There is cause and effect. And I point that out because there's a lot of examples of apparent correlation when there really isn't any. Just because something looks like there's a good line that fits it. So here's what I want you to do. I want you to grab a handful of darts, and I want you to close your eyes and I want you to throw them at the board. Do you realize that it would be impossible for you not to have a pattern that looks linear? Do you realize that? It would be impossible for you to do something and not have a linear pattern, because the only other option is your darts formed a perfect circle. They either formed a perfect circle or they didn't. Do you think they would form a perfect circle? Probably not. So if they didn't, there's absolutely a clear, recognizable linear pattern, yet you just throw darts at a board. There's no line of best. You threw darts at a board. There was no input-output. There was no cause and effect. So to have the illusion of cause and effect just because points look like they're really good doesn't mean you have it. In my stats class, one of the classic examples, and one of my all-time favorites, is there was a study back in the 70s, 80s, I don't remember exactly what year, in the New England part of the world, where they found an unbelievably high correlation between ice cream consumption, some of you probably heard this one, and shark attacks. Anybody ever heard that one? It's classic. It's in every stats book. And they found when ice cream consumption went up, shark attacks went up. When it went down, it went down. So it's like, don't eat ice cream today because, you know. And there's an unbelievably high, you know, what appears to be a correlation. Do you think eating ice cream causes a shark attack? Or better yet, do shark attacks cause people to eat up more ice cream? You say probably not, which means usually in this scenario there's a third variable. It's called a confounding variable. Anybody know what it is? Weather. When it's warm, people go in the ocean and they eat more ice cream. When it's cold, they don't go in the ocean and they don't eat as much ice cream. It's actually that simple. But there's the illusion of cause and effect. Does that make sense to you? There's the illusion of cause and effect. So in reality, you actually have to prove the cause and effect. Otherwise, everything we're doing is a complete waste of time. We're going to assume in our situation that it's already been established there's a cause and effect. X is the input, Y is the output, and we have reason to believe it. Then we can just, you know, come up with our equations. Does that sound good? In a stats class, no, we make more of a big deal about the cause and effect because otherwise it doesn't matter if we come up with the equation with line. It doesn't mean anything. You actually have to know there's an input-output cause and effect situation. So what I want to do is come up with the equation of the line, and we usually write it in this form, which is strange. We say, different books use different letters. We write it backwards. We go, that's not slope-intercept form. Don't we usually put the x first and then the constant? There's a reason that we do it this way. And I'm going to give you the reason. The reason actually comes from statistics. We do problems in Math 119 in a class like this. We do really nice problems. We have one input and one output. One independent variable, one dependent variable. In real life, I couldn't come up with a scenario where there's one independent variable. No, there's always, always, always many independent variables. Okay? Doesn't matter what the situation is, you have multiple things that you input. That'd be like saying all companies produce one product. No, they produce lots of products.
Are we recording?
Oh, are we recording?
Yeah.
We are, right? Okay.
It's blinking red.
Thank you for you made me nervous there for a second. We have multiple, right? Typically inputs. So the formula we use at the upper levels, I've done these problems with multiple independent variables. At the higher levels, we do it usually like this. We'll say the formal line, they'll use b's. So they'll say beta naught plus beta 1x1 plus beta 2x2 plus all the way to beta n xn, because there'll be n independent variables starting with the constant going this way. That's the actual line, and then what we're doing is trying to find the coefficients using our sample information. That's why we use small b's in a stats class. We use Greek b's in a higher level. So what are we doing? We're saying we're just going to go with one independent variable. That's why we write the equation in that form. Because the standard equation actually, you put all the x's this way. You don't put the constant at the end. You put it at the beginning. So we're saying we have one independent variable. The hat means this is going to be our measured answer because we have a few sample points. In reality, we're saying, no, there might be infinitely many data points. There is a line out there. We don't know what it is. We have a handful of points, so this is our best determination of the line. So if you went out and collected information, you got 5 points, you're going to get a line. You got 5 points, you're going to get a different line. Probably similar, but not the same line because you started with different information. If there was actually an underlying best line, we always make that assumption there is, we can't know it without collecting all the data. But that would be like saying I need all the water molecules in the ocean, all human beings on the planet Earth. Well, that doesn't always work, does it? So I do samples. So in our situation, we have n data points. We treat it like a sample. I want to find this piece of cake. Well, here's the thing. If I take the data points and I put them into the equation, I don't know what A0 and A1 are. I know what the data points are. So similar to the polynomial curve fitting, we knew the x and y values, remember? We were trying to figure out what are the coefficients. Well, this is similar in that. We know the x's and y's, so what I'm going to get is a bunch of equations. I'll write it in this form. A0 plus A1 x1 equals y1. A0 plus A1 x2 equals y2, all the way down to A0 plus A1 xn equals yn. I'm going to get n linear equations. I'm not trying to find the x's and the y's. I know those. I'm trying to find the A0 and A1. What I'd like to do is write this as a matrix product. Could we write this as a matrix product? Yeah, that'd be pretty easy, actually. So I'm going to write it this way. What are my unknowns again? A0 and A1, not the x's. Oh, so think of it this way. What's the coefficient of A0? 1. What's the coefficient of A1?
X.
So now look at that, see? A0 plus A1x. A0 plus A, or I should say A1x2. A0 plus A1x3, and so on and so on. Do you see it now? Ah, and what does that equal? So here's my matrix equation. These are all constants, these are all constants, these are my unknowns. So if I multiplied this out, I would get this system of equations, no question about it. Based on my picture, though, that I drew over there, am I going to get a unique solution just off the top of your head? It certainly seems like there's some play involved, right? This line might be this way, it might be this way. It doesn't feel obvious, though, does it? That I'm going to get an easy answer. Turns out, like I said before, as long as not all the x's are the same, this will have a unique solution. I just don't see it yet. Let's call this matrix, for lack of a better name, we'll call this capital X. We'll call this one capital A, and let's call this one capital Y. I'm trying to find capital A. Well, what we saw last week was, if I have the matrix equation and I'm trying to find capital A, don't I just have to multiply both sides on the left by x inverse? Wouldn't that do it? And then I'd get the identity times A, which is just A. Couldn't I just do that?
X is in square.
Oh, you got it. I didn't even get a chance to keep winking. That was when I wink with my left eye, you know something's up, right? X isn't square. Oh, so x inverse does not exist, so that can't really be done. Darn. Well, that was a good thought, but we're not far off, believe it or not. So we're going to be clever. We're going to do something here. There is no x inverse, but there is still a way to undo that equation. So I'm going to show you something. All right? If I said I have an, just in general, let me use a different letter of the alphabet. Matrix Z, how's that? Matrix Z is 2 by n, therefore matrix Z transpose is n by 2. Okay? Z transpose Z, it doesn't really matter which one I call Z. I just generically call them these guys. And Z transpose. What's the shape of Z transpose Z in this picture?
N by N.
N by N. By the way, assume N's bigger than 2. Assume that I'm not starting square. But I know this is square. And what's this guy? 2 by 2. Here's the interesting thing. This inverse does not exist, period, in any context. Assuming N is bigger than 2. It does not exist. It's stuff that we're not going to learn until a little bit later. It has to do with what we're called linearly independent columns and rows and a lot of stuff. But the bigger matrix does not exist. The inverse does not exist. But except in one exception, there's only one exception. By the way, assume these are not zero matrices too. That's really, really boring, okay? Not the zero matrix. There's only one exception. This inverse will always exist. Huh. In other words, the smaller one will always exist. By the way, the only way this inverse does not exist is if the rows and or columns are multiples of each other. That's the only way the inverse won't exist, strangely enough. Yeah, Renton.
If the line is the line of best fit, then why did we assume that the points are going to be on the equation?
Well, no, I'm saying if there is a line of best fit out there, then I'm going to put them on there. You're right. Technically, they're not, but there has got to be some relationship between them. This will allow us to find it. I have to assume there is a line. Okay. Now, technically, the text would usually throw an error. In other words, there's that little cushion, that little gap. They'll call it plus E1, plus E2, plus E3, an error, but the error doesn't go in, ends up not computing into the calculation I'm going to show you. Okay, but you're absolutely right. If none of the points are exactly on the line, then I can't absolutely satisfy the equation, but the equation of best fit, if I put each of the points in there, it will allow me something to solve for. The 2 by 2 inverse will exist. Okay, that's the crazy thing. The big one won't, the small one will. Well, why would I care? Let's go back to here. If this is my X matrix, I was just trying to illustrate something here. If that's X, what's X transpose? Okay. I want a 2 by 2. So I need to multiply the 2 by n by the n by 2, agreed? So in this case, I need to do X transpose X. And when I do X transpose X, I'm going to get a 2 by 2. Boom, 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 boom. 1 plus 1 plus 1 plus 1, how many times? N times. Huh. Then it's going to be X1 plus X2 plus X3 plus X4. Oh, that's just the sum of the X's. But then when I do the other one, it's the same thing. And then when I do the second row, second column, it's X1 squared plus X2 squared plus X3 squared, which is I'm just showing you a result. You're going to physically do this on your own anyway. How many have had Math 119? How many have had it? Do you remember doing linear regression? Do you remember how you do the sum of the X's, the sum of the Y's, the sum of the XY's, the sum of the XY? You did all these things and you just plugged in, I don't know what I'm doing. I'm showing you where they all come from. They all come from what we're about to do here. Now, why is this interesting? Because with one exception, this inverse exists. Okay, so let's suppose we find this inverse. Let's suppose we find X transpose X inverse. Okay, it's a thing. Now, just for fun, can we find X transpose Y also? Well, what's X transpose Y going to look like? Well, that's going to be 2 by 1, because this was a 2 by n and that was an n by 1. So when I do this multiplication, it's going to be y1 plus y2 plus y3 plus y4. Oh, that's just the sum of the y's. And when I do the second row, it is x1, y1 plus, x2, y2 plus. That's the sum of what? The xy's. How interesting, because again, if you've been in stats, those were the things you had to find. The sum of the x's, the sum of the y's, the sum of the xy's, the sum of the x squareds. You didn't need the y squareds though, by the way. They didn't show up. So just for fun, I have this quantity right here. Now, let's go back to our original statement here. This is a quantity here. This is a quantity. just for the heck of it, I don't need this. Let's go back to our weird equation. I have XA equals Y. What if I multiply both sides on the left by X transpose X inverse X transpose? You told me that X transpose does not have, or excuse me, X does not have an inverse because it's not squared. You're absolutely correct. Just for the heck of it, what would happen if I multiply both sides on the left by exactly that quantity right there? Well, then this would read X transpose X inverse X transpose times X times A equals X transpose X inverse times X transpose times Y. I'm going to put the parentheses for readability because remember, although not commutative, matrix multiplication is associative. So you do want to kind of group things. Okay, cool. Does anybody notice something really cool about right now?
We have all those already.
What is that quantity?
Identity.
That's identity, isn't it? I just multiplied X transpose X inverse by X transpose X. And if the inverse exists, this has to be the identity. Which means, guys, we just figured out how to undo this. The inverse of X did not exist, but I multiplied by something that acted like an inverse. Okay? We have just figured out something called the pseudo inverse. Yes, X does not have an inverse. X is not square. But I found a matrix that when I multiplied it on the left, acted like an inverse because it left me with the identity. Does that make sense? So we have just figured out a way A is equal to this quantity right here. Which, by the way, is really, really simple to do always. This is never going to be challenging. These are small matrices. These are 2 by 2s and 2 by 1s. I could give you 1,000 data points. This is still 2 by 2, and this is still 2 by 1. So you guys want to try a problem? Yeah, for that. Let's see. But I love this. This, by the way, when you perform this multiplication, you get the line of best fit. If you go back to your stats book and look at all these really nasty, scary-looking formulas, everything we just did is part of your scary formulas. But you don't know where they came from. You just plug and chug, and then you get an answer and go, okay, but I don't know where they came from. It all came from matrix algebra. All of the stats formulas that you learned in that context come from matrix algebra, strangely enough. All right. So I made a nasty problem. I want to do the nasty problem first. All right, I'm going to give you 5 data points. I don't need to do a million. We want to find the line of best fit for these 5 points. So again, we are starting with the assumption, yes, there is correlation, there is cause and effect, there is input-output, okay? The points are not on the same line, and the points really don't have to be that close to the line. If my points are really far from the line, that means the correlation is weak. If the points are really close to the line, that means they are strongly correlated, but there's always going to be a line. No matter what. If I just said make up points, and here's the funny thing, like I said before, if you just, oh heck, let's put glue on the board and grab a handful of sand. That's a lot of data points, right? How much sand can you fit in your hand? Maybe a few hundred data points? And you throw the sand at the board. Is it going to form an absolute perfect circle? Probably not. Therefore, whatever you see, you will clearly see a linear pattern. Whether there is one or not, you will always see a clear linear pattern. If I said throw 3 darts at the board, either the darts are on the same line or they're not. Do you agree with that statement? Let's suppose they're not. Okay, here's my 3 darts. There's still a line of best fit, and it's right about there. There's always a line of best fit. Okay? So we, again, are assuming there's correlation. We're assuming there's a reason to do this. What I like to do often is I like to draw a picture. You never have to draw a picture. But I like to draw a picture, you know, if the values aren't too great, just to kind of make sure that, you know, when I get an answer at the end, that my answer kind of agrees. In other words, you can use a little common sense and say, oh, my slope should be positive, or my slope should be negative, you know, my y-intercept, things like that. So -5, -4, actually probably let's say there, -2, x, whoops, -4, what did I say? Negative. And -2, 0, maybe about there, and then 1, 7 there, and 4, 2, there, and then 8, 15, maybe about there. Okay, obviously they're not on the same line, but do you see a linear pattern-ish? Yes. Do you see a positive slope? How about y-intercept? Probably also a positive number. That way, when I get done at the end of the problem, if either one of those values disagrees with this, then I know I probably made a mistake somewhere. I mean, clearly these points are going uphill, so I should get a positive slope at the very least. And I'm going to show you there's some really easy checks that you can do at the end to know that you did it correctly. All right, so let's start by labeling our matrices. So let's start with x. 1, 2, 3, 4, 5. -5, -2, 1, 4, 8. And I have x. Let's transpose. And matrix y. Okay. I haven't done any work whatsoever. I just took the points and wrote the matrices that are associated with those points. Okay? Don't make any mistakes here. Don't drop any negatives if you can, you know, avoid that sort of thing. Now there's a couple of matrix multiplications I need to perform. So the first one, I need to do x transpose x, which will be 2 by 2. Well, I know it's going to be a 5. This plus this plus this plus this plus this, 13, that's going to be a 6. And so then that's also a 6. And this squared plus this squared, that's 29, 30, 46, 64, that's 110. Okay, and don't make arithmetic mistakes here, that'll mess you up. Now I need the inverse. What goes in front? So it's 550 minus 36, so that'd be 514. Now, I need to have that inside at some point. I don't feel like doing it yet. I'm lazy. Are any of those fractions going to reduce nicely? 5 over 514? No. I mean, I might cancel an even number somewhere. Here's what I don't want to do. If I put this over 514, 514, 514, 514, 3 of the 4 then will reduce and the other one won't. And that's not necessarily a great idea, because then when I'm multiplying in the next step, I have different denominators. We talked about that before. I'd probably just leave it like this for now. We got to multiply it out. My final answer is going to have obviously 514 in a denominator somewhere. But let's wait. Let's wait to physically throw that in, okay? Now let's do x transpose y. That's going to be a 2 by 1. So sum up the y coordinates. So that'd be 3, 15, that's 30. And then 20 plus 0 plus 7 plus 48 plus 120. So that puts that 27 plus 48, that's 75 plus 120, that's 195. All right, we're almost done. My matrix A, which is the A0, A1. I'll just write it out. Is the product of this times this. Okay, so let's do that. I'm gonna keep the, I'm gonna, again, like I said before, I'm gonna be lazy. I'm gonna keep this in front until after I multiply. It is absolutely correct to have it in and multiply with all the fractions. That's, of course that's correct. What if I told you you had to do this problem without a calculator? You'd probably wait to throw it in, right? It's gotta be in the answer, but when I'm doing the multiplication, I wanna use these numbers first, okay? So tell me what's gonna go here and here. Okay, use your calculator. Don't do that. Don't do that in your head. There's no reason. Anybody?
2130 and 795.
2130, 795. Does that look right? 2130. Is it 795?
Yes.
Okay. So do either one of these quotients reduce? Well, the first one does. Should you reduce it? The answer is it doesn't make any difference. But if I'm going to use my line of best fit to then, now I'm going to give you some input. Now I want you to give me output. Do you agree it'd be easier if I left the denominators the same from that standpoint? Might be. By the way, it's always correct to reduce. Sometimes you get lucky and one of these might reduce to an integer. Well, absolutely you'd want to reduce it to an integer. So what is the answer now? The answer was the line of best fit. We've done all the work. Y hat indicates the line of best fit. It's not the universal line. I only used 5 data points. 2130 over 514 plus 795 over 514x. That's the answer. What if I gave you some input and I said, predict the output? Remember, in a line of best fit, the whole point of a line of best fit is to predict. It's saying, okay, now what if I give you this input, what's the best answer you can give me? You'd give me the Y value that's on the line of best fit. And then in a stats class, you'd then put a cushion around it, a plus or minus. It's called the confidence interval. The closer the points are to the line, the better your guess is, in a sense. The farther they are, the bigger that interval, but that's what we actually do. I'm pretty sure I did all this correct. All right, we good with pretty sure? Now I'm going to show you a really simple way to check this. Okay. Tell me what is the slope between the two furthest apart points? Between here and here, what's the slope? So it'd be 15 plus 4 over 8 plus 5, so it's 19 over 13. Okay? By the way, the answer is fractional. There's nothing wrong changing it to a decimal approximation, but the answer just is icky fractions. Okay. Give me a decimal for 1913s. I'm not really big on 1913s in terms of trying to work it in my head. That's about 1.46. How big is 795 over 514? That's about 1.55. Are those values close? They're very close. Well, why aren't they equal? That would be an absolute and utter impossibility. There is no scenario that exists where they could be equal, because that would mean the line had to actually pass through both of those points. But it ought to be really close. So in my picture, my line of best fit, wherever it's going, that line has a slope a little bit more than 1.5. If I had taken the slope between the two most extremes, we got a number that was very close to 1.5. That's how you can check to see if you did it right. That's not a very formal mathematical check, is it? That's kind of, it's borderline the common sense check. So if I take the two most extreme points of my group of points, whatever slope is between them, I probably am going to see something really close in the actual line. That's how I always check it. Okay? So what if those values were extremely different? Well, it means I probably had a mistake somewhere. But they're really close. I mean, they're less than 0.1 apart. I'd say that's pretty good. Okay? So this is line of best fit, and again, the reason you use this is to be able to make predictions based on information. Yeah, an example I like to use in stats. We've got all of this data, let's say for each year, maybe going back to 2000 and then last year, and maybe it might be tax data or something. And I've got all of this data, and then when I plot it, it's a fairly linear climb. Each year we grew, roughly about the same amount. But I've got some missing years. Maybe I'm missing a year in there somewhere. I can't find 2007 or 2014. Can I use the line of best fit to fill in the blank? Yeah. Yeah, I can use the line of best fit to fill in the blank if it was essentially linear, because it probably wouldn't be very far off. That's the kind of stuff we actually do in real life when there's missing data and there's a pretty good linear relation. You can use the line of best fit to fill it in. Is it good to predict the future with it? Like what's going to happen next year, the year after, the year after? Actually, no, that's not where it's used, unfortunately. In investing in general, do you guys ever pay attention to the commercials when they're investing commercials? There's some lines you always hear, and then always a lot of fine print. But you'll hear things like, past performance, there's no guarantee of future earnings. You ever hear words like that? They're giving you the disclaimer saying, look, just because it did well last week doesn't mean it's going to do well next week. And by the way, if they could tell you how it's going to do next year, go to Vegas, bet on every game that hasn't happened, because if they can predict the future, then it's like Back to the Future when you got the whole sports betting guide, remember? Yeah, bet on all the sports. No, they can say based on past performance, this is the most likely outcome. That doesn't mean it's going to be the outcome. The company might go under next year, who knows? But between the range of values, here's where it works. Between inputs of -5 and +8, I can use this line. So let's do that. Let's suppose that now all of a sudden I found, an input of 3 came along. Can you give me the best possible y value for an input of 3? Well, replace x with 3. Let's do that. For an input of 3, if x is 3, I got a y of approximately 8.8. So for an input of 3, assuming that anything's fair game. Now, what if you could only have integer values? You'd probably go with 9, but don't worry about that. So in other words, my line of best fit said this would be the predicted value for this input. Does that mean that's what it would have been exactly? No, but it probably would have been very close to that. Because now when I go back to my graph, if I do, x is 3, 8.8 is on the line. So obviously it could have been a little higher, could have been a little lower, but probably not terribly far off, because all the other points are essentially linear. That's all. All right, now I want to find something for you. This is just going to take a minute. I'm only going to show you where it is. I'm not going to use this to do the problem today. We're going to do
Can I
some
ask
stuff.
a quick question about
Absolutely.
this? So last week we were using the inverse to solve systems of equations, and it would give us like an exact answer that you could plug back into the original equations. Why, when we use the inverse with this, it just gives you
Well,
a
first of all,
similar...
because there isn't one exact answer, in the sense that I'm not solving a system of equations that has a unique point of intersection. I'm actually doing something different. I'm taking a bunch of points and saying, what's the closest line? So that right there is kind of nebulous already. Plus, I do not get a system of equations that gives me a square coefficient matrix. So what if, let's just have some fun. What if there were only 2 data points? Then essentially, now you're going back to solving the problem that you were talking about. If there's only 2 data points, do you agree there's exactly one line and it passes through both? And now I can tell you what that would be. And now I would be using the inverse and finding exactly the answer. What makes this valuable is I can do more than 2 data points and give you the closest line. This is exceptional. This is not what we were doing before. This is just a tremendous example of using the matrix algebra and the inverse. Is linear regression important? In the stats world, it's considered hugely important. It is one of the more important things, but we're doing linear regression with one independent variable. I've had graduate courses at State where we were doing it with many independent variables, and it can get kind of gnarly, but it's still matrix algebra. It's a lot gnarlier. Let's just leave it at that. It's almost scary, it's so big. All right, so I'm going to show you how to find what we're going to do next. So you don't have to search too much. Let me just see. On my computer in my office, it's one of these automatic things. I don't even have to finish the word and it already goes to the right place. All right. So the next topic that we're going to discuss is something called the simplex method. Yeah, like new technology, all right. All right. Okay, so the simplex method, in mine, we're doing Larson, linear. Okay, 9.3 right here. Once you type it in once, like on my computer, I hit SIM and it automatically goes to this spot. This is the entire section. I hate the scrolling part of it, but everything's here, the explanation, this is all one problem, by the way. I'm saying, this is literally one problem. One of the things the author is guilty of in this section is killing the problem by over-explaining the arithmetic. He literally takes 5 pages to do one problem. We're going to do it in a small space, because I don't need to explain to you how to add 2 numbers together and where they go. We're going to do it, and you're going to be fine. But then here's the practice problems that you're going to need. We're going to do 9.3 over the course of today. I'm going to introduce it, and then we're going to do a bunch next day, and 9.4, which is kind of a harder version. 9.3 is the main one. This method, it's absolutely beautiful. So when you type in, you can go to Cengage and type it in, and it'll probably take you there. Okay. A number of years ago, does anybody have their physical copy with them? If you look in your table of contents, it will have the other chapters, but it'll tell you how to get there. Now, the problem the older books had was because it was Pearson, then it's Cengage, and I think they maybe sold it again, you would go there and it was a dead end because the company kept changing. So you notice it has 10 chapters, but your book only has 7. So where does it tell you to go here? But it says cengagebrain.com, but I just need you to type in simplex. You just want to go right to the spot. You don't want the whole chapter, you just want the section right there. Chapter 8, which is one of the more important chapters in your mathematical lives. It's the complex version of chapter 7, which is the most important chapter in the book. Chapter 8 we will also cover at the very end of the course. That's how we finish the course. And then we will come back to this. So we're going to spend 2 days on chapter 9, then we're going to spend 2 days at the end of the course on chapter 8. But you'll know how to find things really, really easily. This is not bootleg. This is the publisher uploaded this kind of stuff. Not, people say, oh, I found a bootleg version of the book. Well, I'm not really supposed to tell people that. That's like saying, yeah, and I also bootlegged my Disney Plus and my HBO Max, and I figured out a way to mess with the cable so I can get all these things for free. Yeah, I don't know that I'd want to tell anybody that. Because it is illegal. Okay. Now, I'm done with this now. Okay, so I'm going to give you the problem that you guys did, probably in pre-calc, maybe in an intermediate algebra class. It comes from a branch of algebra called linear programming. This is in every algebra and pre-calculus book, but the instructor may or may not have chose to cover this stuff. Linear programming is when you have a system of inequalities and you want to solve or find something. So I'm going to give you the Reader's Digest version. This is the problem you probably all remember from mathematical children. Okay, Farmer Jones produces 2 crops, peas and corn. He might make $100 per acre of peas and $150 per acre of corn. Now, he's got 1,000 acres available. It costs $25 to plant an acre of peas and $50 an acre of corn, and he has $10,000 available. it requires 8 hours to plant an acre of peas and 12 hours to plant an acre of corn, and he's got 3,000 hours of work available. How many should he plant of each to maximize his profits? Does that sound vaguely familiar to anyone? Now, here's the thing. What a lot of people don't realize, and I said this in all seriousness, is the further you go on in math and life, you realize rarely are things actually equals. Rarely are things actually equations in real life. Most things actually are inequalities. Has anyone handled the budget at their job before? You were in charge of writing the checks, anything. Okay, so they gave you a certain amount of money. Last day of the month, there's still $10,000 left. Oh my gosh, what am I going to do? I got to spend it. Do you have to spend it? In fact, would they be happy if you don't spend it? Huh. You go to the store later on today, you have 20 bucks in your pocket, you go in, and it's $19.50. You go, oh, darn, I got to go back and find 50 cents worth of stuff. I had a fun one yesterday in my stats class. You're allowed to miss 6 questions on the written portion of the driving exam. And Brian's pretty sure he got them all right. Oh man, I gotta go back and find 6 to miss. In other words, each one of those are inequalities. We don't speak in inequalities, by the way. Nobody speaks in inequalities. You can miss 6. No, you can miss at most 6. When you had $20 at the store, you can spend at most $20. You got to get 90% of this course to get an A. Darn it, Duke was at 95%. Sorry, Duke. You had to be at 90 to get an A. Or was it at least 90? In other words, it was 90 or more. You guys understand how often that you speak in words that sound like equals when actually the intent was inequalities, and you don't always use at most and at least in your, right? When you're on the freeway and the sign says 65, what do you say? Yeah, at least. I like that. Actually, I think it's the other one. But it doesn't mean you have to drive exactly 65. Now, I always bring up the next one. It's kind of painful. I almost feel like I should turn this one off. There aren't that many ladies in the class. Oh my goodness. The guys understand this one. I've noticed over there's the girls don't. My oldest daughter at 12 was the same height she is now. Both of my boys, who are much taller than me now, were the smallest kids in their high school on the first day of 9th grade. They were both the shortest and the smallest, and now they're big men. Guys often grow a little later. So you remember that you were with some youth group, maybe it was a church group or a YMCA group or just something, and you went to the amusement park. The sign, the evil cardboard cutout clown. Oh yeah, I can see it. You must be this tall to ride the ride. You guys know what I'm talking about? You were 12, 13 years old, and you weren't that tall. All the girls were that tall because they'd all stopped growing. You weren't. My oldest son, every year his school went to Legoland, and every year he couldn't ride that roller coaster-ish ride because he wasn't tall enough. So his last year of eligibility, he got smart. He stuffed his shoes with wads of newspapers. He literally took an entire newspaper, stuffed it with wads of, gave him an extra inch, and of course, gelled his hair and spiked it. And he made it by the slimmest of margins. He literally fudged 2 inches so he could finally ride that ride. Now, you're bigger than the clown. So does that mean you can't ride the ride? I mean, do you go like this? No. When it says you must be this tall to ride the ride, what is it saying? You must be at least that tall. Again, that evil cardboard clown, I know most of you want to destroy it and strangle it because it caused you so much grief and suffering. And I'm not even going to ask because I know some of you, you're going to go home and back to therapy and stuff. You finally got over. I know this is a fact. When my boys would ask me, "Oh, am I ever going to grow?" Yeah, they did. Yeah, they're huge now. But the point being that everything we do is an inequality. So when Farmer Jones has 1,000 acres, does Farmer Jones have to use all 1,000 acres? No, 1,000 or less. Everything that I just said when I was talking about conditions, they're called constraints. Every one of them was an inequality. Okay? So I'm going to give you a situation where we're going to solve a problem. And I'm going to give you the formal language that we use. Okay? I want to maximize. Now, I'm just picking random things. think of Farmer Jones peas and corn crops to give it some context. I want to maximize, let's say, profit equals 4 times x plus 6 times y. This could be acres, and this could be dollars. Maybe this is $4 million. I don't know, $4,000 could be $4. Doesn't matter. I want to maximize this quantity subject to the following constraints. That x plus 2y is less than or equal to 108. That 2x plus y is less than or equal to 72. That 4x plus y is less than or equal to 128. And x and y are both non-negative. So if you want to think about this, acres of peas and corn, I can't have a negative number of acres, can I? All real numbers would suffice, by the way. There's no restriction that says they have to be integer values. They just have to be non-negative. Now, this could be this could be, how many hours of work available. This is how much money is available. It could be whatever you want it to be. I'm just going to give you a system of inequalities. Now, what makes a system of inequalities particularly difficult is there cannot be a unique solution. So I'm going to start the way we did it when we were kids, and that is to graph it, because that's the only way we ever learned how to do this. So I'm going to draw a rough sketch of what I got here. Since x and y are both non-negative, that means that all of my regions, okay, should be in the first quadrant. Do you agree? Because I'm not going to have anything here, here, or here. So so the first thing you do is, if you solve for the y, this is going to be y is less than or equal to negative a half x plus 54. So I'm just going to kind of loosely, it's kind of go like that. Then the next line, y is less than or equal to negative 2x plus 72. That's going to kind of, again, don't worry about the accuracy of my drawing. It's about that. That point is important. The next line is going to be y is less than or equal to 4x plus 128. That's going to intersect way the heck up there. I'm just going to go like that. Okay? They're all inequalities. Now, if you remember from baby algebra, when graphing an inequality, let me give you a really simple one. Okay? This is baby algebra. X plus y is greater than or equal to 3. Which side do I shade? A lot of people think they have a system. That's the easiest thing in the world. Pick any point on the entire xy plane that is not on the line. Now, if you know me, you know my favorite number is always what to check?
0.
Always use 0. So why not use the origin? It's hard to screw this up if I use the origin. Is 0 plus 0 greater than 3? The equal would be the points on the line. I picked a point on the line. Is this true or false? It's false. That means every point on the same side as 0, 0 will also be false. Here's an absolute with inequalities. Every point on one side either makes it true or makes it false. Every point. That's why you only have to check one. 0, 0 made it false. That means I shade the other side. That's it. Some people say, well, I look at the inequality. You better not just look at the inequality, because I could write an inequality that's this where you shaded the other side. So don't just look at the inequality. Look where things are, in other words. So going to here, in each case, if I use 0, 0, 0, 0 makes this true, 0, 0 makes this true, 0, 0 makes this true. What does that mean? 0, 0 made all of these true, which means I've enclosed a polygon. Now, this should feel vaguely familiar to you. You did this problem a million years ago. This system of inequalities combined with x and y being non-negative forms this. How many ordered pairs are in that polygon? Infinitely many. Now, do you guys remember where the solution must come from?
Where they all intersect.
Well, they don't have a common point of intersection, though, but there are points of intersection. For example, these two lines intersect here. These two lines intersect here. This is the x greater than or equal to 0. It intersects here. So I have a bunch of vertices. Now, this part is never explained to my satisfaction. We'll figure out what they are in just a moment, by the way. I have 5 vertices. The answer has to come from one of those. And it's actually a Calc 3 thing. Ooh. Now, think Calc 1 for a moment. Now, I'm going to explain in really simple terms why you know this, because this is, I've never seen this explained in any textbook, no matter what level. In Calc 1, I want to maximize, minimize, right? Remember inflection points, extremely, you're doing all that stuff. I give you a simple graph. And you know, take derivative, set equal to 0, do all this stuff. But what if you have a closed interval? That's extreme value theorem. We like extreme value theorem. Because in a closed interval, extreme value theorem says that as long as the function is differentiable throughout the interval, in other words, I don't have any asymptotes, any weirdness is going on, as long as basically I have this interval, there's always going to be an absolute max and there's always going to be an absolute min, and it must come from where? Critical values or endpoints. And that's a wonderful check when you're doing application problems, because applications often, you know, I got to be from here to here, I have closed intervals. So the extreme value theorem says I must get endpoints or critical values. Now in Calc 3 we do the same thing, okay? But we're in 3D, so that's the one, if you were in my class, you have to use the Hessian and you have to do all that stuff. And there's still going to be extrema, and there's, you know, but intervals get to be a little more crazy. So let's look at this not as a Calc 3 problem, but as a Calc 1 problem. I am bounded, I have particular constraints, but would you say that all of these would be closed intervals? I mean, these lines are not going forever. So all of my lines are closed intervals. This is only from here to here. Now, if I have a line as a boundary, will that line have a critical value if I take a derivative? No, it's a line. So the extrema on a line segment, the extrema can only come from the endpoints. So simple calculus says, since my boundaries are basically line segments, and line segments will have no critical values because the derivative of a line is always a constant, that means the extrema can only come from the endpoints. So using calculus as the argument, my extrema can only come from the endpoints. Well, can't it come from the middle? It could if the function I was maximizing had more going on. In other words, my derivatives are all constants, are they? So I'm not going to get any critical things in the interval because everything's linear. I will only get critical values if it's nonlinear. Because when I take the derivative of a nonlinear function, I may be able to set that to 0. All my derivatives would be of linear functions, so all my derivatives are constants. None of my derivatives will ever be 0. So there's no interesting things happening in the middle. So now I look at the boundaries. Again, this is Calc 3 argument. I look at the boundaries, so my extrema must come from the boundaries, but because derivatives are never 0, my extrema must come from the endpoints. This is the reason why when you did this, you only considered the vertices. Because the calculus says your answer can only come from the vertices. Because you have no critical values. And that should be a kind of a, oh, okay, that makes sense. They couldn't tell us that in pre-calc because we didn't know what derivatives were. And it's technically really a Calc 3 argument more than a Calc 1 argument. So let's figure out these points of intersection, shall we? I already did. Okay. This is 0.54. This is 12.48. This is 28.16. This is 32,0, and this is 0, 0. I have 5 points of intersection. Now, I don't know where the answer comes from because that is entirely dependent on these coefficients. Hypothetically, if I make the coefficient on the x huge in comparison to the y, my answer is probably coming from here. If I make the coefficient of the y huge compared to the one of the x, the answer is probably coming from here. If I make the x and y coefficients relatively close together, then the answer is probably coming from one of these two. Does that make sense? If I then, maybe I change the sign of one of them, make a negative, technically the answer could come from here. Probably not. So when I'm maximizing, you more think of it going this way. I want x and y to be as big as they can, but I'm limited. Next day we're going to talk about the minimization problem. So that's a more complicated problem. So I've got these. Here's what we did in baby algebra. And I just gave you each point. I'll start with 0, 0, 0.54. I'm going to go around in a circle. 12.48, 28, 16, 32, 0. And let's find P for each of these. I'll do that. That's 128. That's 0. We got that one down. This is 324. 48 was 288. That'd be 336. And what would this one be? 96 plus 112. That'd be 208. So do we have a winner? Sort of a winner, winner, chicken dinner up here, I think. Would it be that one? So I will maximize my profit if I do 12 of the 12 x's and 48 y's. I don't have to change the coefficients very much to have the answer be something else. Do you agree with that? In fact, go up and down. I could even make it, one of them was negative. That would really affect things. Okay? So it's really, all things are possible, and this is how you get the problem. You say, well, this didn't require any tremendous math skill. You know, I basically think of those as being equations and find out where the equations intersect. That's where my vertices come from. Do you notice that this vertex here is not relevant? Because it's outside the region. That's important to recognize. You say, well, this, why would we talk about this in a linear algebra class? Because Farmer Jones got a big, huge government subsidy loan. And guess what? He now has 4 crops. Well, can't we just do this? Please get back to me on the 4-dimensional graphs. Oh, in other words, this problem only works when you have 2 independent variables. What if there's more than 2? Well, I'll just get out my holographic thing and set up all of my planes that intersect and, you know, have a 3-dimensional drawing. But what about the 4th and 5th and 6th variables? There is a way of doing this that doesn't matter how many variables you have. It does not involve drawing a picture. That's what the simplex method is. That's what we're about to do right now. And it's very cool. Now, I saw a proof of this when I was in grad school at UCSD, and my brain still hurts, and, you know, a few presidents ago. I'm not going to do the proof. I'm going to do the demonstration of the simplex method, which is actually really, really simple. But it's very different. It's a very different form of matrix algebra than you've ever seen, because your goal is quite different, and the rules are very different. I'm going to leave that picture up there because I want to do the same problem. A problem where you already know the answer. Because what I do now with 2 variables is exactly what I'm going to do when there's 3 or more. The method's the same regardless of the number of variables. So what we do, we start with that problem right there, and I take the original 3 things here, and I make equations out of them. Because you cannot use a matrix to solve a system of inequalities. You can only use a matrix on a system of equations. But how do I create equations? We introduce something called slack variables. We're going to make up variables, insert them into the problem for the purpose of doing the problem, and then we're all done, we get rid of them. They're not part of the final answer. See, I want to make this an equality. This is less than or equal to 108. So if I added the right amount, I could make it equal. So my first equation is going to be x plus 2y plus s1 equals 108. My second equation is going to be 2x plus y plus s2 equals 72. My third equation is going to be 4x plus y plus s3 is 128. And then the last one, kind of weirdly, I'm going to throw those on the other side and write it as negative 4x, negative 6y plus p equals 0. And now I'm going to do a matrix using these. You with me so far? It's kind of a crazy idea. Now, I have x, I have y, I have s1, I have s2, and I have s3. I now have 5 variables. P is not a variable. P is not a variable. So don't make a y, because P is just a linear combination of the x and the y. You're not solving anything. P is just the end of the problem. When you find your x and y, then you're going to calculate P. But I need this. So here's my matrix. 1, 2, 1, 0, 0, 1, 2, 1, 0, 1, 0, 72. 4, 1, 0, 0, 1, 128. Negative 4, whoops, negative 4, negative 6, 0, 0, 0, 0. This is my starting matrix. If this is not absolutely correct, I can't get the right answer because I'd be doing a different problem, essentially. Now, I'm not going to do things the same way. We don't do our pivots as the upper left. We actually select our pivots through a simple algorithm that I'm going to show you next. And then we go from there. So each column here represents a variable. I'll write it above just to remind you. That represented the x, that's the y, that's the S1, the S2, the S3. Okay? Your answer can only come from a unit column. A unit column, think of a unit vector. That's a unit column, 1, 0, 0, 0. That's a unit column, 0, 1, 0, 0. That's a unit column. Everybody okay with that? Your answer can only come from a unit column. And when you have a unit column, the answer is basically what's on the other side. So if I stopped right now, S1 would be 108, S2 would be 72, S3 would be 108, and every column that is not a unit column, the value of that variable is 0. Okay? If you have a lot of variables, it's not unusual to have a variable have a 0 at the end. So if I stopped right now, I would read my answer as x is 0 and y is 0 because they're not unit columns. And therefore, all 108 went to the slack variable. All 72 went to the slack variable. All 128 went to the slack variable. I produced no crops. So what's my profit going to be? That's kind of boring because we actually haven't done anything. But is that a viable solution to do absolutely nothing? Yeah. And that was my first answer in the lower left corner. So as we go through the process, there will be complete cycles. And I'm going to show you at the end of each cycle, you will always get a viable solution. You'll get something that actually works. Will it be the final answer? Not necessarily. You're not done until you're done kind of thing. So the way you do it is, on the bottom row, you look at the largest negative number. That means my pivot's going to come from the second column. Now, look at the ratio, 108 over 2, 72 over 1, 128 over 1. We take the smallest positive ratio. If you take a negative ratio, if one of those was negative, by the way, it's absolutely okay to have negatives in the problem. If one of those was a negative ratio and I used it, my final answer would be so far from reality it wouldn't even be funny. If I have a 0 in there and you use it, you used something over 0 that's undefined, and that again, if I use the wrong number, I will get the wrong answer. But if I use something that doesn't even make sense, it's total whack. Now, 108 over 2, 72 over 1, 128 over 1. Which is the smallest of those? 108 over 2? So I'm going to circle it. There's our first pivot. Since the goal is to create unit columns, I have to make that into a 1. Okay? Now, this is an algorithm. All human beings doing this problem actually have to have exactly the same things at the same time. This is not one like a regular matrix where you have maybe options, right? I could do this or this or this, and then I go from there. Everybody has to do the same thing. Everybody has to select that value because of the algorithm that we just used. So I'm going to take half of row 1. So I have a half, 1, a half, 0, 0, 54, and then 2, 1, 0, 1, 0, 72, then 4, 1, 0, 0, 1, 128, negative 4, negative 6, 0, 0, 0, 0. Now, I like to circle my pivots. And I do this so I don't forget which number I'm using. It's really easy to all of a sudden go to the wrong value of 1. Do you see multiple 1s up there? Yeah, you will actually make that mistake occasionally. You'll go to the wrong place. Okay, you kind of forget where you are. So I want to put zeros below it. So how about negative row 1 plus row 2, negative row 1 plus row 3, and 6 row 1 plus row 4. Now, negatives would be 3 halves, 0, negative a half, 1, 0, 18. The negatives would be 7 halves, 0, negative 1 half, 0, 1, 74. Now when I do 6 of these, I'd do negative 1, 0, 3, 0, 0. I did 6 of these, so that's now 324. Okay? We've just finished the first cycle. Am I done? No. Here's how you know you're not done. You're not done if there are any negative values on the bottom row. It's only the bottom row that I'm worried about. This is the first line of the problem. I have 2 negatives on the bottom. If I had no negatives on the bottom row, I'd already be done before I started the problem. You're done when there's no negatives. I still have a negative on the bottom row, so that means I'm probably going to have to do one more cycle. Which makes sense. I only have 2 variables. 2 cycles probably is a good thing. Now, if I stop right now, do I have a viable solution here? Yes. The first column was x, so x would be 0. The second column is y, so y would be what? 54. If x is 0 and y is 54, folks, if x is 0 and y is 54, then what's my problem? If x is 0 and y is 54, and that's what's sitting there right now, isn't it? I'm not done because of this, but I have a viable solution. I moved on my graph. Now, what about the slack variables? This would say x is 0 and y is 54. It would also say that I still have 72 unused S2s, and I still have I'm sorry, this wasn't the wrong one. Sorry, this one. I have 18 unused S2s and 74 unused S3s. Okay? If x is 0 and y is 54, then S1 would be 0, wouldn't it? That means, think of S1 being 0, meaning I used all of that resource. Okay? But if x is 0 and y is 54, don't I have 18 unused here? That says that S2 would be 18. If x is 0 and y is 54, doesn't that mean I still have 74 unused whatever S3 represents? And that's what you can read from there. So the slack variable, think of as the unused portion of whatever my resource is. Could be time, could be money. Okay, that's literally what it would represent. Because we said you don't have to use up everything. You just can't. When you have, this is the most you can spend. You just can't exceed it. You can always come in short, but you can't exceed it. So you don't always have to use up your resource. Okay, so there can be unused resources. So now, the next round, I start here. So 54 over a half, that's 108. 18 over 3 halves, that's 12. 74 over 7 halves, that's 148 sevenths, that's more than 20. Which is the smallest? I think it's the 18 over the 3 halves. So that becomes my next pivot. The arrow, I'm telling you, it's the first column, that's the smallest ratio, so there's my pivot. I need that to be a 1, so I'm going to do 2/3 of row 2. Now you're going to need your calculators. 1/3, 2/3, and 12. And it stays the same, 1, 1/2, 0, 0, 4, 7 halves, 0, negative a half, 0, 1, 74, and negative 1, 0, 3, 0, 0, 3, 24. Okay? This should be the end of the problem, the next step. I need that to be a unit column, so I'm going to go up and I'm going to go down. So I'm going to do negative a half of row 2 plus row 1. I'm going to do negative 7 halves row 2 plus row 3. And I'm going to simply do row 2 plus row 4. All right, so 0. And the reason I say use your calculator now, because you're taking fractional multiples, potentially of fractions, and adding them to other fractions that don't necessarily have the same denominator. Yikes, okay? This is the stuff where we tend to make lots of mistakes on. So negative a half, that would be 0, 1. Negative half, that's a 6 plus a half, that's 2/3. Negative a half, so that'd be negative a third. 0, 48. Negative 7 halves, that'd be 0, 0. Negative 7 halves times negative a third. It's negative 7, 6. So what does that come out to be? Or, sorry, negative 7 halves, so that'd be positive 7, 6. Minus 3, 6, that's 4, 6, or 2/3. Negative 7 halves would be negative 7 thirds. 1, negative 7 halves, so that'd be what? What would negative 7 halves of 12? Is that right? 12? Yeah. It'd be negative 42, so I think that would be 32. And then finally adding these guys, 0, 0, 8 thirds, 2 thirds, if I didn't make any mistakes here, 0 and 3/36. You're going to make arithmetic errors. You can't afford them because it may lead to incorrect answers, because the numbers on the right I might make mistakes on also. Now, unit column, no negatives on the bottom. Am I done? Yes, I am now done. How do I read my answer? The first column was x, so x equals what? 12. The second column was y equals 48, and my profit, 336. Same answer? Crowd goes wild, confetti everywhere, dancing in the streets. Well, of course we're supposed to get the same answer. But I wanted you to notice how we're kind of moving around the outside. Had I given you a different set of coefficients here, obviously it would have changed our answer. It would not have changed the strategy, mind you. The strategy I used would have still been essentially the same, but it would have changed the numbers a little bit. Now, there's no S in my final answer. But did I use up all my resources? If x is 12 and y is 48. X is 12 and y is 48. So that's 12 plus 96 equals 108. Yeah, I used up all those. X is 12 and y is 48. So that'd be 24 plus 48. That does equal 72. So I used up all of those, didn't I? That's 1 and S2. There's nothing left. X is 12. Y is 48. That's only 96. Ooh. That means whatever the third one represented, I had a lot left over. That might be hours of labor. That might be money to plant the crops. That might be, whatever that other resource was. Do you notice? There's my S3 column. S3 was 32. That just simply means I did not use up all of my resources. Because I have multiple inequalities, it's more common than not that you would have leftover whatever. You can think of it another way. As I'm planting, I might run out of money before I fill up all my acres. Or I might run out of labor before I run out of money. There's a lot of things you could run out before. Not everything's going to run out at the exact same time. That's probably not very realistic. So what we're going to do next day is we're going to do 3 variable problems. 3 or 4 variable problems. And I'm going to show you, it's the same process, we just don't bother with a picture because we can't. Kind of cool, because the arithmetic's really simple, but the goal and the strategy are quite different. We're using a matrix on a system of equations where we created the system of equations by introducing these things called slack variables to literally whatever the unused portion was. That's the easiest way of thinking of it. And at the end of the problem, my answer does not include the slack variables, but I just showed you the justification. Okay, yeah, 2 of the 3, we used everything up, and the other one we would have had some left over, whatever that represented. Okay?